Right now, as you're watching this video, there are approximately 400 billion stars in our galaxy alone. Around many of those stars orbit planets. Some of those planets sit in what we call the habitable zone, the perfect distance from their star where liquid water can exist on the surface. And where there's liquid water, there's the possibility of life. So here's the question that has haunted humanity for thousands of years, the question that drives billions of dollars in research, the question that might fundamentally change what it means to be human. Are we alone in the universe? It's a simple question with staggering implications. If the answer is no, if life exists elsewhere, it would be the most profound discovery in human history. It would tell us that life isn't a cosmic accident, that the universe is teeming with biology, that we're part of something much larger than ourselves. But if the answer is yes, if we're truly alone in this vast cosmos, that might be even more terrifying. It would mean that consciousness, intelligence, civilization, everything we've built and discovered and created exists in one tiny corner of an otherwise dead universe. We'd be the only ones watching, the only ones asking questions, the only ones seeking meaning in the void. Today, we're going to explore this question from every angle. We'll look at the mathematics that suggest life should be common. We'll examine the evidence that suggests we're alone. We'll discuss why we haven't found aliens yet, what that might mean, and what we should do about it. By the end of this video, you won't have a definitive answer, because nobody does, but you'll understand why this question is so complicated, why it matters so much, and why the search for extraterrestrial life might be the most important scientific endeavor humanity has ever undertaken. Let's start with the math. Undersöker, Part 1, The Numbers Game. Chapter 1, The Drake Equation, our first attempt at calculating. Aliens. In 1961, astronomer Frank Drake organized the first scientific meeting on the search for extraterrestrial intelligence. Before the meeting, he wanted a way to structure the discussion, so he wrote down an equation. It wasn't meant to give a definitive answer. It was meant to organize our ignorance. That equation became known as the Drake equation, and it looks like this: NYR X, FP X, NX, FL X, FI X, FC X, L. Let me break that down. N is the number of civilizations in our galaxy with which we might be able to communicate. And to calculate N, we multiply several factors. R is the rate of star formation in our galaxy. How many new stars are born each year? We actually know this one pretty well, about 1.5 to 3 stars per year. FP is the fraction of those stars that have planets. When Drake first wrote this equation, we didn't know if planets were common or rare. Now we know. Nearly every star has planets. This number is close to 1, maybe 0.8 to 1. NE is the number of planets per star system that could potentially support life, planets in the habitable zone with the right conditions. Based on what we've discovered with telescopes like Kepler, this might be around 0.4 to 2. So far, we're doing okay. We have decent estimates for these numbers. But now it gets harder. FL is the fraction of planets that could support life where life actually develops. This is where we hit our first wall of ignorance. Life appeared on Earth remarkably quickly, within a few 100 million years of the planet cooling enough to support it. Does that mean life is easy and inevitable? Or did we just get incredibly lucky? Some scientists say FL is close to 1. Life emerges wherever it can. Others say it's vanishingly small. Life requires such specific conditions that it's rare in the universe. We have a sample size of 1, so we genuinely don't know. FE is the fraction of planets with life where intelligent life evolves. Again, we only have Earth as an example. Life existed on Earth for about 3.5 billion years before anything we'd call intelligent emerged. Does that mean intelligence is rare and difficult to evolve? Or does it mean it's inevitable given enough time? We don't know. FC is the fraction of intelligent civilizations that develop technology we could detect. Radio signals, visible megastructures, obvious signs of industry. On Earth, we've had detectable technology for maybe 100 years out of 4.5 billion years of planetary history. Is that normal? Are most intelligent civilizations non-technological? Do they develop technology but not the kind we can detect? Again, we don't know. And finally, L is the longevity of detectable civilizations. How long does a civilization last before it destroys itself, evolves beyond detection, or just goes quiet? This is the most terrifying variable in the equation because it might tell us something about our own future. If L is small, if most civilizations last only a few hundred years after, developing radio technology, that might mean we're doomed. That technological civilization is inherently unstable and self-destructive. If L is large, thousands or millions of years, that's more optimistic. It means civilizations can survive their technological adolescence, but we have no idea which it is. Here's what's interesting. Depending on what values you plug into the Drake equation, you can get wildly different answers. If you're optimistic about all the unknowns, you get thousands or even millions of communicative civilizations in our galaxy right now. If you're pessimistic, you get a number less than 1, meaning we're alone in the Milky Way, possibly alone in the observable universe. The Drake equation doesn't give us an answer, but it does something important. It shows us exactly where our ignorance lies. It tells us what questions we need to answer, and scientists have been trying to answer those questions ever since. Chapter 2. The Fermi Paradox. Where is everybody? The Drake equation suggests that intelligent life might be common in the universe, but in 1950, physicist Enrico Fermi asked a simple question that has haunted scientists ever since. Where is everybody? This is the Fermi Paradox. If intelligent life is common, why haven't we seen any evidence of it? Let's think about this logically. Our galaxy is about 13.6 billion years old. The universe is 13.8 billion years old. That means there's been plenty of time for intelligent civilizations to arise, develop technology, and spread across the galaxy. In fact, let's do some rough math. If a civilization developed interstellar travel and expanded outward at even a fraction of the speed of light, say 1% the speed of light, they could colonize the entire galaxy in just a few million years. A few million years sounds like a long time, but it's nothing on cosmic scales. The galaxy has been around for billions of years. If even one civilization developed interstellar travel billions of years ago, they should have spread everywhere by now. We should see evidence of them. Megastructures around stars, artificial signals, terraformed planets, industrial waste heat. Something. But we don't. We see nothing. The universe appears completely silent and devoid of intelligence, except for us. This is deeply weird. It's like showing up to a party that should be packed with people, but finding the place completely empty. Either everyone's hiding, or something's wrong with your assumptions. The Fermi Paradox has generated dozens of proposed solutions, and we'll explore many of them in this video. But the basic tension is this. The numbers suggest aliens should exist and should be obvious. But observations suggest we're alone. Something doesn't add up. Chapter 3. How we've looked for aliens. So far. Before we get into why we haven't found aliens, let's talk about how we've been looking. The most famous search is SETI, the search for extraterrestrial intelligence. Since the 1960s, scientists have been pointing radio telescopes at the sky, listening for signals that might be artificial rather than natural. The idea is simple. If there's a technological civilization out there, they might be broadcasting radio signals, either deliberately to communicate with other civilizations or accidentally as a byproduct of their technology. Earth has been leaking radio signals into space since we invented radio technology. Our TV and radio broadcasts, radar systems, and other transmissions radiate outward into space. An alien civilization with sensitive enough equipment could detect these signals from dozens of light years away. So SETI listens, hoping to hear the alien equivalent of our radio leakage or, even better, an intentional message. The most famous SETI event was the WOW signal detected on August 15, 1977. The signal was so strong and unusual that the astronomer reviewing the data wrote "wow" in the margin. It appeared to come from the direction of the constellation Sagittarius, lasted 72 seconds, and has never been detected again. Was it aliens? Probably not. It was most likely a natural phenomenon we don't fully understand, or possibly interference from Earth-based sources. But for a moment, it seemed like we might have detected something extraordinary. Since then, SETI has analyzed billions of radio signals. They've found nothing definitively artificial, no "Hello Earth" messages, no obvious patterns that couldn't be explained by natural phenomena. But SETI is limited. We're only listening to a tiny fraction of the sky, at a tiny fraction of possible frequencies, and we can only detect signals that happen to be pointed in our direction when we're listening. It's like trying to find a specific conversation in a city of billions of people by standing on one street corner with a directional microphone tuned to one radio station for a few minutes. If you don't hear anything, does that mean nobody in? The city is talking. Recently, efforts like Breakthrough Listen have massively expanded SETI's capabilities, using more telescopes, covering more of the sky, and analyzing more frequencies. But we still haven't found anything. We've also looked for aliens in other ways. We've searched for technosignatures, signs of industrial activity or megastructures. We've looked for biosignatures in exoplanet atmospheres, combinations of gases that might indicate biological activity. In 2015, a star called KIC 8462852, also known as Tabby's star, made headlines because its light dimmed in weird, irregular patterns that some speculated might be caused by alien megastructures. Turns out it was probably just dust, but for a while, it seemed like we might have found something. We've sent physical probes too. The Pioneer and Voyager spacecraft carry plaques and golden records with information about Earth and humanity, just in case they're ever found by aliens. They're now in interstellar space, cosmic messages in bottles. And we've sent deliberate messages. The Arecibo message, transmitted in 1974, was a radio message sent toward a star cluster 25,000 light-years away. It contained information about humanity and Earth encoded in binary. Of course, even if aliens receive it and respond immediately, we won't hear back for 50,000 years. Interstellar communication is slow, but despite all these efforts, decades of listening, looking, and searching, we've found nothing. Not a single confirmed signal. Not one verified piece of evidence for extraterrestrial intelligence. Which brings us back to the question, why? Chapter 4. The Great Filter. Are we early, or are we doomed? One of the most discussed solutions to the Fermi paradox is the concept of the Great Filter. This idea, popularized by economist Robin Hanson, suggests that there's some barrier or filter that prevents life from becoming a spacefaring, galaxy-colonizing civilization. The question is, where is this filter? If the filter is behind us, if it's the step from non-life to life, or from simple life to complex life, or from complex life to intelligence, then we're lucky. We've already passed the hard part. The universe might be filled with bacteria, but empty of intelligent civilizations because intelligence is incredibly rare and difficult to evolve. This would be good news for us. It would mean our future is relatively secure. We're special. We've made it past the hardest challenges, and now we can expand into the cosmos. But if the filter is ahead of us, that's terrifying. It would mean that something happens to almost all technological civilizations that prevents them from colonizing the galaxy. Maybe they destroy themselves with nuclear weapons. Maybe they create AI that wipes them out. Maybe climate change makes their planets uninhabitable. Maybe there's some technology or phase of development that's inevitably deadly. If the Great Filter is ahead of us, finding alien life would actually be bad news. Because it would mean the filter is later than we thought, and we haven't reached it yet. Think about it. If we discover microbial life on Mars, that tells us that the step from non-life to life is easy. The filter isn't there. If we find evidence of complex life elsewhere, that tells us multicellularity is easy. The filter isn't there either. Every time we find life elsewhere, we narrow down where the great filter must be. And if it's not behind us, it's ahead of us, waiting. This is why some scientists have argued that, paradoxically, we should hope we don't find alien life, because finding it increases the probability that the great filter is in our future. There's a darker interpretation of the great filter hypothesis, too. Maybe the filter isn't something that happens to civilizations. Maybe it's something civilizations do to each other. Maybe the reason we don't see advanced civilizations is because whenever a civilization reaches a certain level of technology, older civilizations detect them and destroy them to prevent competition. Maybe the galaxy is dominated by a civilization, or civilizations that actively suppress the development of new technological species. This is sometimes called the dark forest hypothesis, after the science fiction novel. The idea is that the universe is like a dark forest where everyone is hiding because revealing your presence is suicide. If this is true, our radio signals, our Voyager probes, our deliberate messages, all of it might be a catastrophic mistake. We might be announcing our presence to predators. Most scientists don't take this hypothesis very seriously, but it's impossible to rule out completely. And it's a chilling thought. Chapter 5. Maybe life is common, but intelligence is rare. Here's a possibility. Maybe the universe is teeming with life, but almost none of it is intelligent. Life appeared on Earth almost as soon as conditions allowed it, about 3.8 to 4 billion years ago. That suggests that the step from non-life to life might be easy. Given the right conditions, chemistry tends toward biology, but life stayed simple for most of Earth's history. Bacteria and archaea dominated for billions of years. Complex, multicellular life only emerged around 600 million years ago. And intelligent life? That's brand new, just a few million years, depending on how you define intelligence. Out of 4 billion years of life on Earth, intelligence has existed for less than 0.1% of that time. And technological civilization? That's only existed for a tiny fraction of a percent. What if this is normal? What if the universe is full of planets with bacteria, full of planets with simple multicellular organisms, maybe even full of planets with animals and ecosystems? But intelligent technological life is vanishingly rare? This would explain the Fermi paradox perfectly. There's no signal to detect because almost nobody has developed the technology to send signals. There's some evidence supporting this idea. Intelligence might not be as evolutionary advantageous as we think. Humans are intelligent, yes, but we're also the only species on Earth that developed this level of intelligence. Out of millions of species, over hundreds of millions of years, it happened once. Compare that to other evolutionary innovations. Eyes evolved independently dozens of times. Flight evolved at least 4 times. But human-level intelligence, once. Maybe intelligence is just one possible evolutionary strategy, and not even a particularly common or successful one. Bacteria have been around for billions of years and will probably outlast us. They don't need intelligence. They're already winning the evolutionary game. Maybe intelligence is actually maladaptive in the long term. It allows for rapid technological development, which creates rapid environmental change, which creates existential risks. A less intelligent species might have better long-term survival prospects because they can't create nuclear weapons or climate change. If intelligence is rare and possibly maladaptive, that would explain why the universe seems empty. Chapter 6. Maybe we're looking in the wrong place or the wrong way. Here's another possibility. Aliens exist, but we can't detect them because we're looking in the wrong place or using the wrong methods. SETI assumes that aliens use radio signals, but what if they don't? What if they discovered some form of communication we haven't even thought of? We've only had radio technology for about 100 years. What if there's something better that we'll discover in another 100 or 1,000 years? If aliens are even slightly more advanced than us, they might be using communication methods we can't detect or don't recognize. It's like trying to find modern humans by looking for smoke signals. You might find some people using smoke signals for fun or tradition, but you'd miss the vast majority of human communication happening. through fiber optic cables and satellites. Or maybe aliens do use radio, but not in ways we expect. Maybe they use highly directional beams that never happen to point at Earth. Maybe they use frequencies we haven't thought to check. Maybe their signals look like noise to our detectors. There's also the possibility that we're looking at the wrong time scale. Civilizations might only be detectable for a brief window in their development. If they exist for millions of years but only broadcast radio signals for a few thousand of those years before moving on to something else, the chances of us looking at the right star at the right time are tiny. Or maybe we're looking at the wrong places. We focus on sun-like stars with Earth-like planets in habitable zones. But what if life is more diverse than that? What if it can thrive in environments we consider hostile, under the ice of frozen moons, in the atmospheres of gas giants, around dim red dwarf stars? We're looking for life as we know it, but life as we don't know it might be much more common and much stranger. There's also the sobering possibility that aliens exist, but they're simply too far away for us to ever detect them. The universe is unimaginably vast. The observable universe contains about 2 trillion galaxies. Each galaxy contains billions of stars, but the speed of light is limited. Information can only travel so fast. If the nearest alien civilization is in another galaxy, millions of light years away, we might never know they exist because their signals haven't reached us yet and might never reach us. Even within our own galaxy, distances are enormous. If an alien civilization is on the far side of the Milky Way, their radio signals would take 100,000 years to reach us. And that's assuming they're broadcasting in all directions at maximum power for that entire time. Space is big, really big, and that bigness might be enough to explain why we seem alone even if we're not. Part 2. The Rare Earth Hypothesis. Chapter 7. What makes Earth special? Let's pivot and consider a different possibility. Maybe we haven't found aliens because Earth is genuinely special, and planets like ours are extraordinarily rare. This is the Rare Earth Hypothesis, proposed by Peter Ward and Donald Brownlee in their 2000 book. They argue that while simple life might be common, complex life requires such a specific set of conditions that it's extremely rare in the universe. Let's look at what makes Earth unusual. First, our Sun. The Sun is a G-type main sequence star, yellow, stable, long-lived. Most stars in the galaxy are red dwarfs, smaller and cooler than the Sun. Red dwarfs are common and long-lived, which sounds good for life, but they're also prone to massive flares that could sterilize nearby planets. They're also so dim that their habitable zones are very close to the star, which means planets would likely be tidally locked, one side always facing the star, one side always dark. Could life exist on a tidally locked planet with one scorching side and one frozen side? Maybe, but it's harder. Second, our orbit. Earth orbits at just the right distance for liquid water. Too close, and water boils away. Too far, and it freezes. This habitable zone exists around every star, but it's narrower for some stars than others. And Earth's orbit is nearly circular. If it were highly elliptical, we'd swing between extreme temperatures, making stable climate difficult. Third, our moon. Earth's moon is unusually large relative to our planet. It was formed by a massive collision early in Earth's history, and it has several important effects. The moon stabilizes Earth's axial tilt. Without it, Earth's tilt would vary wildly over time, causing extreme climate swings. The moon also creates tides, which may have been important for early life and definitely influenced the development of life in coastal areas. Most planets don't have large moons. Earth might be unusual in this regard. Fourth, our magnetic field. Earth has a strong magnetic field generated by its liquid iron core. This field protects us from solar wind and cosmic radiation, which would otherwise strip away our atmosphere and irradiate the surface. Mars probably once had a magnetic field, but it shut down, and Mars subsequently lost most of its atmosphere. Without our magnetic field, Earth might be similarly barren. Not all planets have strong magnetic fields. It depends on their internal structure and composition. Fifth, our atmosphere. Earth's atmosphere is about 78% nitrogen, 21% oxygen, and trace amounts of other gases. This composition is crucial for life as we know it, but it's also partly created by life. Oxygen is a waste product of photosynthesis. But we also need an atmosphere that's thick enough to keep the planet warm and protect the surface from radiation, but not so thick that it creates a runaway greenhouse effect like Venus. Getting this balance right might be rare. Sixth, plate tectonics. Earth's crust is divided into plates that move around, creating mountains, volcanoes, and ocean trenches. Plate tectonics recycles nutrients, regulates atmospheric composition through volcanic outgassing and weathering, and might be necessary for maintaining a habitable climate over billions of years. We don't know how common plate tectonics is. Venus doesn't have it. Mars might have had it briefly. It might require specific conditions of planet size, composition, and internal heat. Seventh, water. Earth has vast oceans, but not so much water that the entire planet is ocean. Having continents and oceans might be important for the development of complex life. Too little water, and you're a desert planet. Too much, and you're a water world with no land. The amount of water Earth has, covering about 71% of the surface, might be in a sweet spot. Eighth, Jupiter. Our solar system has Jupiter, a massive gas giant that acts as a gravitational shield, deflecting many asteroids and comets that might otherwise hit Earth. Some scientists think that having a Jupiter-like planet in the outer solar system might be necessary to reduce bombardment and allow complex life to develop, but having Jupiter is also dangerous. If it were closer or larger, it might disrupt Earth's orbit. You need the right kind of gas giant in the right place. Ninth, our galactic location. The Sun orbits in the galactic habitable zone, not too close to the center, where radiation and gravitational disturbances are dangerous, and not too far out, where heavy elements needed for rocky planets might be scarce. We're in a relatively quiet neighborhood, which might be important. 10th, the timing. Earth formed about 4.5 billion years ago, when the universe was already over 9 billion years old. Early in the universe, there weren't enough heavy elements to form rocky planets. We needed previous generations of stars to live, die, and spread heavy elements through supernova explosions. But we also can't wait forever. Stars don't last infinitely, and the universe is expanding and cooling. There's a window of time when conditions are right for complex life, and we might be in it. When you add all these factors together, you start to see that Earth might be unusually lucky. Not impossible to replicate, there are billions of planets in the galaxy, so even rare conditions should occur sometimes. But maybe rare enough that complex life is scattered thinly across the cosmos. If the rare Earth hypothesis is correct, simple microbial life might be common, but complex multicellular life, and especially intelligent life, might be so rare that we're effectively alone in the observable universe. This would explain the Fermi paradox. We don't see aliens because there aren't many to see. Part 3. Life in our own backyard. Chapter 8. The search for life in our solar system. Before we look to distant stars, let's talk about our own cosmic neighborhood. Because if we're going to find evidence of life beyond Earth, the most likely place might be right here in our solar system. This might sound surprising. After all, we've sent probes to every planet, landed on some of them, and haven't found any little green men. But the search for extraterrestrial life isn't just about finding intelligent aliens. It's about finding any life at all. Even bacteria would be revolutionary. And there are several places in our solar system where life might exist right now. Let's start with Mars. The red planet has fascinated humanity for centuries, and for good reason. Mars was once much more Earth-like than it is today. Billions of years ago, Mars had liquid water on its surface, a thicker atmosphere, and possibly a magnetic field. conditions might have been suitable for life. We know this because of the geological evidence. Mars has ancient riverbeds, lake beds, and what appear to be ocean shorelines. Water flowed on Mars, possibly for hundreds of millions of years. So here's the question. If Mars was habitable billions of years ago, did life emerge there? And if it did, is it still there? Mars today is cold, dry, and bathed in radiation. The surface is hostile to life as we know it. But life might survive underground, protected from radiation, possibly accessing liquid water that exists beneath the frozen surface. We found strong evidence of subsurface water on Mars. In 2018, scientists detected what appears to be a lake of liquid water beneath the Martian south polar ice cap, about a mile underground. If that water is really there, it's a potential habitat for microbial life. The Mars rovers, Spirit, Opportunity, Curiosity, and Perseverance, have all searched for signs of past or present life. They've found organic molecules, which are the building blocks of life, though they can also form through non-biological processes. Curiosity detected seasonal variations in methane in Mars's atmosphere. On Earth, most methane is produced by living organisms. On Mars, it could be geological, but it could also be biological. We don't know yet. Perseverance, the newest rover, is currently collecting samples that will eventually be returned to Earth by future missions. Those samples might finally answer whether life ever existed on Mars. But Mars isn't the only potentially habitable world in our solar system. In fact, some of the most exciting targets for finding life are the moons of Jupiter and Saturn. Europa, one of Jupiter's moons, is covered in ice. But beneath that ice is an ocean, a global ocean of liquid water that might contain twice as much water as all of Earth's oceans combined. How do we know this? Through careful observation and modeling. Europa's surface shows cracks and ridges that suggest the ice is floating on liquid water. The moon's interaction with Jupiter's magnetic field is consistent with a conducting fluid, like salty water beneath the surface, and Europa has energy. The tidal forces from Jupiter flex and squeeze the moon, generating heat through friction. This tidal heating keeps the subsurface ocean liquid despite being so far from the sun. So Europa has liquid water and energy, two of the three ingredients for life. The third ingredient is chemistry, the raw materials. We don't know exactly what Europa's ocean is made of, but observations suggest it might have the necessary chemical complexity. If life exists in Europa's ocean, what would it look like? Probably not fish or whales. More likely, it would be microbial, possibly similar to the extremophile bacteria that live near hydrothermal vents in Earth's deep oceans. On Earth, these deep-sea vents support complex ecosystems completely independent of sunlight. They run on chemosynthesis rather than photosynthesis, using chemical energy from the vents instead of light energy from the sun. Europa's ocean might have similar vents where the rocky seafloor meets the water. If so, it could support life. NASA is planning a mission called Europa Clipper, set to launch in 2024, that will conduct detailed reconnaissance of Europa. It won't land, but it will fly by multiple times, analyzing the moon's ice shell and searching for signs of life. There's also talk of a future mission that would land on Europa and drill through the ice to access the ocean directly. That's technologically challenging and decades away, but it's the kind of mission that could definitively answer whether life exists there. Enceladus, a moon of Saturn, is another compelling target. Like Europa, Enceladus has a subsurface ocean, but Enceladus gives us easier access to its ocean water. The moon has geysers at its south pole that shoot water vapor and ice particles into space. The Cassini spacecraft flew through these plumes and analyzed their composition. It found water, organic molecules, and evidence of hydrothermal activity, exactly what you'd want for life. Enceladus is smaller than Europa and farther from the sun, but it might actually be a better target for finding life, because we can sample its ocean water without drilling through miles of ice. We just have to fly through the plumes. Titan, Saturn's largest moon, is weird and wonderful. It's the only moon in the solar system with a thick atmosphere, and it has liquid on its surface. Not water, but liquid methane and ethane. Titan has lakes, rivers, and rain, but it's all hydrocarbons. Could life exist in liquid methane instead of liquid water? We don't know. Life as we know it requires liquid water because water has special properties that make it ideal for biochemistry. But that doesn't mean life in other solvents is impossible. Some scientists have speculated about weird life that could exist on Titan, life with a fundamentally different chemistry from Earth life. It would be slow and cold. Titan's surface is 290 degrees, but it might be possible. We won't know until we look more closely. NASA is planning a mission called Dragonfly, a rotorcraft that will fly around Titan exploring its surface and searching for signs of life. It's set to launch in 2027 and arrive in 2034. Even Venus, Earth's hellish twin, might have habitable zones. Venus's surface is hot enough to melt lead with crushing atmospheric pressure and clouds of sulfuric acid. Not friendly, but high in Venus's atmosphere, about 30 miles up, conditions are surprisingly mild. The temperature and pressure are similar to Earth's surface, and liquid water droplets might exist in the clouds. In 2020, scientists announced the detection of phosphine in Venus's atmosphere. On Earth, phosphine is produced by anaerobic bacteria. Its presence on Venus was controversial. Some scientists questioned whether it was really detected, and even if it was, whether it required a biological explanation. Follow-up observations have been mixed, and the debate continues. But it raised the possibility that microbial life might exist floating in Venus's clouds, something nobody had seriously considered before. The point is, our solar system might not be as dead as we thought. There are multiple worlds with the ingredients for life. If we find life on Mars, or Europa, or Enceladus, that would tell us something profound. That life is not rare, that it emerges wherever conditions allow. And if life emerged independently twice in one solar system, that would strongly suggest the universe is full of life. Chapter 9. The building blocks are everywhere. One of the strongest arguments for the existence of extraterrestrial life is that the building blocks of life are everywhere in the universe. By building blocks, I mean the chemical ingredients: water, organic molecules, energy sources. These aren't rare or exotic. They're common throughout the cosmos. Let's start with water. Water is made of hydrogen and oxygen. Hydrogen is the most abundant element in the universe, created in the Big Bang. Oxygen is created in stars and spread through space when stars die. The result is that water is everywhere. We've found water ice on Mars, on moons throughout the outer solar system, on asteroids, on comets, in interstellar clouds, and in the atmospheres of exoplanets. Water isn't precious in the cosmic sense, it's common. Organic molecules, molecules containing carbon, are also widespread. We've detected them in interstellar clouds, in comets, in meteorites that have fallen to Earth, and in the atmospheres of planets and moons. These aren't just simple molecules either. We've found amino acids, the building blocks of proteins, in meteorites. We've found complex organic molecules in interstellar space. Life requires organic chemistry, and organic chemistry happens naturally throughout the universe. Energy is also available in many forms. On Earth, most life runs on sunlight through photosynthesis, but we've discovered ecosystems that run on chemical energy instead, the deep-sea vent ecosystems I mentioned earlier. These ecosystems prove that life doesn't require sunlight. It just needs some form of energy to drive chemical reactions, and energy is available everywhere, from stars, from radioactive decay, from tidal heating, from chemical reactions. The universe is not a sterile place. It's full of the raw materials for life. Chemistry happens. Complex molecules form. The conditions for life exist in many places. This doesn't prove life exists elsewhere, but it removes one potential objection. We can't say life is rare because the ingredients are rare. The ingredients are common. So if life doesn't exist elsewhere, It's not because the chemistry is impossible or the materials are unavailable. It must be because some other step is difficult, maybe the step from chemistry to biology, or from simple life to complex life, or from life to intelligence. Chapter 10: Exoplanets. Thousands of new worlds. In 1992, we discovered the first exoplanet, a planet orbiting a star other than our sun. It was a weird discovery. The planet orbited a pulsar, a rapidly spinning dead star, not a place you'd expect to find planets, and definitely not a place where life could exist, but it proved that planets exist around other stars. And once we started looking seriously, we found them everywhere. Today, we've confirmed over 5,000 exoplanets, with thousands more candidates waiting for confirmation. We've found planets of every imaginable type, hot Jupiters orbiting close to their stars, super-Earths, larger than Earth, but smaller than Neptune, ice giants, lava worlds, and yes, potentially habitable rocky planets in the habitable zones of their stars. The Kepler Space Telescope, launched in 2009, revolutionized exoplanet science. It stared at one patch of sky continuously for years, monitoring 150,000 stars and detecting planets by the tiny dimming of starlight when a planet passes in front of its star. Kepler found that planets are common. Nearly every star has planets. The galaxy contains hundreds of billions of planets. More importantly, Kepler found that Earth-sized planets in habitable zones are not particularly rare. Based on Kepler's data, astronomers estimate that there might be tens of billions of potentially habitable planets in our galaxy alone. Tens of billions. Let that sink in. Now, potentially habitable doesn't mean inhabited. It just means the planet is roughly Earth-sized and orbits at a distance where liquid water could exist on the surface. But it's a start. Some of these planets are tantalizingly interesting. Proxima Centauri b, orbiting the nearest star to our Sun, is roughly Earth-sized and sits in the habitable zone. It's only 4.2 light-years away, close by cosmic standards. The TRAPPIST-1 system, about 40 light-years away, has 7 Earth-sized planets, 3 of which are in the habitable zone. This system is so interesting that it's a prime target for the James Webb Space Telescope. Kepler 4552b orbits a Sun-like star in the habitable zone and is about 60% larger than Earth. It's 1,400 light-years away, so we're not visiting anytime soon, but it's potentially Earth-like. The question is, do any of these planets have life? We can't answer that yet. We're still developing the technology to analyze exoplanet atmospheres in detail, but we're getting there. The James Webb Space Telescope, launched in 2021, can analyze the atmospheres of some exoplanets by studying the starlight that passes through them. Different molecules absorb light at different wavelengths, creating a spectral fingerprint. If we detect certain combinations of gases, oxygen and methane together, for example, it might indicate biological activity. On Earth, oxygen is produced by photosynthesis, and methane is produced by bacteria and other organisms. Finding both together on an exoplanet would be suggestive, though not definitive proof. We're also looking for other biosignatures. Oxygen alone might indicate life. Unusual ratios of gases might indicate life. Seasonal changes in atmospheric composition might indicate life. This is the frontier of astrobiology, analyzing distant worlds from afar, searching for chemical clues that life exists there. Within the next decade or two, we might detect biosignatures on an exoplanet. We might find strong evidence that life exists beyond Earth, or we might not. We might analyze dozens of potentially habitable planets and find no signs of life, which would tell us something important too. That habitable doesn't mean inhabited, that the step from chemistry to biology is harder than we thought. Either way, we're living in the first generation of humans who can actually search for life on other worlds. That's remarkable. Part 4. The Zoo Hypothesis and Other Wild Ideas. Chapter 11. Maybe they're watching us. Here's a weird idea that some scientists take seriously. Maybe aliens exist, maybe they know about us. and maybe they're deliberately not making contact. This is called the zoo hypothesis, and it suggests that Earth is essentially a nature preserve or zoo that advanced civilizations observe but don't interfere with. Why would they do this? Several possibilities. Maybe there's a galactic ethical code that prohibits contacting primitive civilizations. Like the Prime Directive from Star Trek, advanced civilizations might have rules against interfering with less developed species. They might think contact would be harmful to us, that it would disrupt our natural cultural and technological development. Or maybe they think we're not ready, that we'd react badly to learning we're not alone. Maybe they're studying us scientifically. We're a young civilization, interesting to observe. They're watching our development the way we might watch a colony of ants, with curiosity but without direct intervention. Or maybe they're waiting for us to reach some threshold of development before they reveal themselves. Maybe there's a galactic community, and you only get invited once you've proven yourself capable of interstellar travel, or peaceful coexistence, or some other milestone. The zoo hypothesis is impossible to prove or disprove, which makes it frustrating from a scientific perspective. But it does explain the Fermi paradox. We don't see aliens because they're hiding from us on purpose. There's a related idea called the planetarium hypothesis. This suggests that what we see isn't real, that advanced civilizations have the technology to manipulate our observations, so we see an empty universe, even though it's not. Why would they do this? Same reasons as the zoo hypothesis. They don't want us to know about them yet. This sounds like paranoid conspiracy theory territory, and most scientists don't take it seriously, but it's technically possible, and it would explain the observations. Another variation is the interdict hypothesis. Maybe there's a powerful civilization or alliance of civilizations that actively prevents contact with primitive species like us. They might destroy any attempt at contact, enforce radio silence, and generally keep young civilizations isolated. Again, impossible to prove, and it sounds like science fiction, but it's logically possible. Chapter 12. Maybe they evolved beyond us. Here's another possibility. Maybe advanced civilizations exist, but they're so far beyond us that we can't recognize their activities, or they're simply not interested in things like radio signals. Think about it this way. A civilization 1,000,000 years more advanced than us might be as far beyond us as we are beyond ants. Would we even recognize their technology as technology? We look for radio signals and megastructures because that's the technology we understand. But a 1,000,000-year-old civilization might use forms of communication and energy that we can't detect or wouldn't recognize. Maybe they communicate through quantum entanglement or gravitational waves or some other method we haven't discovered yet. Maybe their engineering is done at the atomic or subatomic level, creating no obvious signatures. Maybe they've uploaded their consciousness into computers and live in virtual realities, their physical presence minimal and hard to detect. Maybe they've transcended physical form entirely in ways we can't imagine. There's also the possibility that advanced civilizations just aren't interested in expansion and communication. We assume that intelligence leads to curiosity, exploration, and the desire to spread across the galaxy. But what if that's a human bias? What if other intelligences have different values and motivations? Maybe once a civilization reaches a certain level of development, they become focused on internal experiences rather than external expansion. Maybe they achieve a state of contentment or enlightenment where they have no desire to colonize the galaxy. They might exist, they might be advanced, but they're just sitting quietly on their homeworlds, not bothering to build detectable megastructures or broadcast signals. We'd never find them because they're not trying to be found. Chapter 13. The Simulation Hypothesis. Okay, this one gets really weird, but it's been seriously discussed by philosophers and physicists, so let's address it. Maybe we're living in a computer simulation. The argument goes like this. If it's possible to create realistic simulations of universes with conscious beings inside them, then advanced civilizations would probably create many such simulations. If there are many simulated universes and only one real universe, then statistically, we're more likely to be in a simulation than in the real universe. And if we're in a simulation, that might explain why the universe seems empty. Maybe the simulators only bothered to simulate Earth and its immediate surroundings in detail. The rest of the universe might be low-resolution filler, empty because it's not the focus of the simulation. Or maybe the simulators don't want simulated beings, us, discovering evidence of other life because that would complicate the simulation. So they've programmed the universe to appear empty, even if the real universe outside the simulation is full of life. I know this sounds like something out of the Matrix, and I'm not saying it's true. Most scientists are skeptical, but it's an interesting thought experiment, and it's technically unfalsifiable. We can't prove we're not in a simulation. If we are in a simulation, it would explain a lot of weird things about physics and the Fermi paradox, but it also raises more questions than it answers. Chapter 14. Maybe they're here and we don't realize it. Let's talk about UFOs, or as they're now officially called, UAPs, Unidentified Aerial Phenomena. For decades, UFO sightings were dismissed as hoaxes, misidentifications, or delusions. The scientific community wanted nothing to do with UFO research because it seemed unserious. But in recent years, that's changed somewhat. The US government has acknowledged that military personnel have observed objects exhibiting flight characteristics that don't match any known technology. Some of these observations are backed by multiple sensors: radar, infrared, visual confirmation. In 2021, the Pentagon released a report on UAPs that confirmed there are objects performing maneuvers, sudden acceleration, hypersonic speeds without signatures, transmedium travel that we can't explain. Does this mean aliens? No. Most UAPs are probably mundane: drones, weather balloons, optical illusions, sensor glitches, but some small percentage remain unexplained. The scientific approach is to investigate without jumping to conclusions. Maybe these unexplained UAPs are secret military technology from rival nations. Maybe they're rare atmospheric phenomena. Maybe they're sensor errors we don't understand yet. Or maybe, and this is a very small maybe, some of them are extraterrestrial. The problem with the UFO hypothesis is that it requires extraordinary evidence. If aliens are visiting Earth regularly enough to be observed by military pilots, why don't we have better evidence? Why no crashes with recoverable technology? Why no clear, unambiguous contact? The answer might be that they're very good at not being detected, or that they're not here regularly, just occasional visitors, or that governments are hiding evidence, though massive conspiracies are hard to maintain, or, more likely, UFOs aren't aliens. There's something else. But here's what's interesting. The scientific community is finally taking UAPs seriously enough to study them properly. NASA has commissioned a study. Scientists are developing methodologies for investigating unexplained aerial phenomena. This is good. If there's something genuinely anomalous happening, we should study it scientifically. And if it turns out to be mundane, that's fine too. At least we'll know. The UFO question is separate from the broader question of whether aliens exist. Even if every UFO is explained as something mundane, aliens could still exist elsewhere in the universe. But if even one UAP turned out to be extraterrestrial, that would be the most important discovery in human history. So we should look seriously, without prejudice, but with appropriate skepticism. Part 5. What it would mean to find them. Chapter 15. The cultural impact of contact. Let's say we find them. Let's say we detect an unambiguous radio signal from an alien civilization, or we discover microbial life on Mars, or a probe from an alien civilization shows up in our solar system. What happens next? The answer depends on what we find. But any discovery of extraterrestrial life would have profound impacts on human culture, religion, philosophy, and our understanding of our place in the universe. Let's start with the least dramatic scenario. We find microbial life on Mars or Europa, simple single-celled organisms, not intelligent, not technological, just alien bacteria. Even this would be revolutionary. It would prove that life is not unique to Earth, that abiogenesis, the process of life arising from non-life, has happened at least twice. If it happened twice in one solar system, it's probably happened countless times across the universe. The universe would almost certainly be full of life, even if most of it is microbial. This would change biology. We'd have a second example of life to study, potentially with different biochemistry. Maybe it uses different amino acids, different genetic codes, different cellular structures. Studying alien biology, even simple alien biology, would teach us about the universal principles of life versus the accidents of Earth's particular history. It would also shift philosophy and religion. Some religious views hold that humans are special, created uniquely by God. Finding alien life wouldn't necessarily contradict this, but it would require theological adjustment. Many religious thinkers have already grappled with this question and concluded that alien life is compatible with their faiths. God could have created life on multiple worlds, but it would still be a significant moment for religious communities. Now let's consider a more dramatic scenario. We detect a radio signal from an intelligent alien civilization. This wouldn't give us direct contact immediately. Radio signals travel at the speed of light, so if the civilization is 1,000 light years away, any message exchange would take 2,000 years round trip. Conversation is impossible, but we'd know. We'd know for certain that we're not alone, that somewhere out there is another civilization, another intelligence, another perspective on the universe. The cultural impact would be enormous. It would be front-page news for months or years. Every human culture would have to grapple with what it means. Some people would be excited, seeing it as the greatest discovery in history. Others would be afraid, worried about what the aliens might want or do. Some religious groups might embrace it, while others might reject it. Science would be transformed. We'd spend massive resources trying to decode the signal, learn about the alien civilization, and possibly send a response. And even without direct communication, just knowing they exist would change us. We'd know that intelligence can survive and persist for millennia or longer, that civilizations can make it through the dangerous phase we're in now. Or, depending on the signal, we might learn that they didn't make it. If we detected a civilization's signals from 1,000 years ago, but they've gone silent since, that would be ominous. It would suggest the Great Filter is ahead of us too. The most dramatic scenario would be direct contact. An alien probe arrives in our solar system, or aliens show up in person. This would be unprecedented. Everything would change overnight. First contact protocols exist. Scientists have thought about how to handle this scenario, but the reality would be chaotic. Governments would scramble to respond. The public would react in unpredictable ways. The nature of contact would matter enormously. If the aliens were peaceful, curious, and willing to share knowledge, it could lead to a new era of human development. They might share technology, answer fundamental questions about the universe, welcome us into a galactic community. Or they might be indifferent, viewing us the way we view animals, interesting, but not worthy of real engagement. That would be humbling and frustrating. Or they might be hostile. This seems less likely. Why would they travel across interstellar space just to attack us? But it's possible. If they wanted our resources or our planet, we'd be in serious trouble. Most scientists think hostile aliens are unlikely. Any civilization capable of interstellar travel would have access to abundant resources in space. They wouldn't need to conquer Earth, but we can't know for sure until it happens. Chapter 16. What we should do. Given everything we've discussed, what should humanity be doing about the question of alien life? First, we should keep looking. The search for extraterrestrial life, both intelligent and microbial, should be a scientific priority. This means continuing seedy observations with ever more powerful and comprehensive surveys, sending missions to Mars, Europa, Enceladus, Titan, and other potentially habitable worlds in our solar system to search for life directly, building better telescopes to study exoplanet atmospheres and search for biosignatures, developing new methods for detecting alien technology and biology. Some people argue that this is a waste of money. We have problems here on Earth: poverty, climate change, disease. Why spend billions searching for aliens? But the search for life costs very little compared to other expenditures. NASA's budget is less than 0.5% of the US federal budget. SETI programs cost even less. We can afford to do both: solve Earth's problems and search for life elsewhere. And the search has benefits beyond finding aliens. Space technology development has given us GPS, weather satellites, medical devices, and countless other innovations. The pursuit of fundamental knowledge drives progress. Second, we should think carefully about whether and how to send messages to aliens. This is controversial. Some scientists, including Stephen Hawking before his death, warned against actively trying to contact aliens. If there are malevolent civilizations out there, advertising our presence might be dangerous. Others argue that we've already announced our presence through our radio and TV broadcasts, so it's too late to hide, and that the potential benefits of contact outweigh the risks. There's an ongoing debate about active SETI or METI messaging. Extraterrestrial intelligence. Should we deliberately send powerful, targeted messages to nearby star systems, or should we listen quietly? Currently, there's no international consensus. Some organizations have sent messages. Others think we should establish global protocols before doing more. Personally, I lean toward caution. Until we know more about what's out there, maybe we should listen more than broadcast. Third, we should prepare for the possibility of contact, even if it's unlikely. This means developing protocols for what to do if we detect a signal. Who responds? What do we say? How do we make decisions on behalf of humanity? These questions sound silly until you realize we don't have good answers. There are proposed protocols, but they're not binding and haven't been tested. We should also think about the societal impact. How would we handle the cultural, religious, and psychological effects of discovering aliens? How do we prevent panic or conflict? These are questions that require input from scientists, philosophers, ethicists, policymakers, and the public. Fourth, we should be honest about our ignorance. We don't know if aliens exist. We don't know if life is common or rare. We don't know if intelligence is inevitable or a fluke. We don't know if we're early in the universe's timeline or late. All we have are hypotheses, probabilities, and educated guesses. That's okay. Science is built on uncertainty and the quest to reduce it. We should embrace the mystery while working to solve it, and we should resist the temptation to either assume aliens definitely exist or definitely don't exist. Both positions are premature, given our current evidence. Nurture Church, Part 6, The Cosmic Perspective. Chapter 17, The Anthropic Principle and Observer Selection Effects. There's a philosophical argument that might explain why we haven't found aliens, and it's both simple and mind-bending. We exist, therefore we must find ourselves in a universe capable of producing observers. This is called the anthropic principle, and it comes in different strengths. The weak anthropic principle says that we shouldn't be surprised to find ourselves in a universe with conditions suitable for life, because if conditions weren't suitable, we wouldn't be here to observe it. It's like a lottery winner being amazed at winning. Yes, the odds were tiny, but someone had to win, and only the winner is around to be surprised. Applied to aliens, maybe intelligent life is incredibly rare, so rare that in most galaxies, it never appears. But it had to appear somewhere, and we happen to be in that somewhere. We're the lottery winners, and there's no one else to observe their non-existence. The strong anthropic principle goes further, suggesting that the universe must have properties that allow observers to exist, otherwise there would be no universe to observe. This gets into multiverse theory and quantum mechanics and becomes very speculative, but here's a related concept that's important: observer selection effects. An observer selection effect is a bias in what we can observe because our existence as observers requires certain conditions. For example, We might wonder why Earth seems so perfectly suited for life. The answer might be that we can only exist on a planet suited for life. If we evolved on a different planet, we'd be asking the same question about that planet. Similarly, with the Fermi paradox, maybe we're asking, where is everybody, from a biased perspective? We exist, which means we're at a point in space-time where intelligent observers exist, but maybe intelligent observers are so rare that most places and times in the universe don't have them. We can only observe from where we are, and where we are is necessarily special because we're here. This doesn't solve the Fermi paradox, but it suggests we should be cautious about generalizing from our existence to the prevalence of life elsewhere. Chapter 18. The Timeline of the Universe. Let's zoom out and think about cosmic timescales, because they might tell us something important about why we seem alone. The universe is 13.8 billion years old. That seems old, but compared to the future lifetime of the universe, it's incredibly young. Stars like our sun will continue forming for trillions of years. The universe will remain hospitable to life for an unimaginably long time, until the last stars burn out, perhaps 100 trillion years from now. So we're living in the first 0.014% of the universe's potential lifespan. Now here's a question. Are we early or late? If intelligent life is common and tends to arise as soon as conditions allow, then the universe should already be full of civilizations that formed billions of years before us. We'd be late, and we should see evidence everywhere. But we don't, which suggests either life is rare or we're early. Maybe the universe is only now reaching the point where complex life commonly emerges. Maybe the first few billion years were necessary to build up heavy elements through stellar nucleosynthesis. Maybe habitable planets only became common recently. If we're among the first intelligent civilizations in the universe, that would explain the silence. There's nobody out there yet because it's too early. This is actually somewhat optimistic. It means the great filter is behind us. We've passed the hard steps, and the universe's future will be filled with life and intelligence as more civilizations emerge. But it also means we have enormous responsibility. As potentially one of the first technological civilizations, our actions might influence how the galaxy develops. Do we spread life and intelligence across the cosmos, or do we destroy ourselves before we can? There's another timeline issue worth considering: the question of how long civilizations last. If technological civilizations typically exist for only a few hundred or thousand years before destroying themselves or going quiet, then the galaxy might have hosted thousands or millions of civilizations over billions of years, but never many at the same time. It's like trying to find other people in a vast building where everyone shows up at random times for brief visits. You might never encounter anyone even though the building is frequently used. This is the brief window hypothesis. Civilizations exist, but they're separated by time rather than space. We're ships passing in the night, never overlapping. If this is true, the galaxy might have ruins, dead civilizations that rose and fell before we existed. We might even find archaeological evidence of ancient alien civilizations if we look carefully at planets or moons in our solar system or nearby stars. The search for alien artifacts or technosignatures from extinct civilizations is a legitimate scientific endeavor, though it's in its infancy. Chapter 19. What alien life might actually look like. Let's talk about what aliens might be like if they exist. Because science fiction has given us very specific images: humanoids with funny foreheads, little gray creatures with big eyes, tentacled monsters, but reality is probably stranger. First, let's address the elephant in the room. Would aliens even be biological? Advanced civilizations might have transitioned from biological to artificial forms. They might upload their consciousness into machines, or create AI that outlives and surpasses them. If most advanced civilizations become post-biological, we might be looking for the wrong thing. We're searching for biological signatures and organic civilizations, but the galaxy might be full of machine intelligence. Machine intelligence would have different needs and behaviors They might not need habitable planets. They could thrive in the vacuum of space or on airless worlds. They might not use radio. They might communicate through methods we can't detect. They might not even be recognizable as life or intelligence. A sufficiently advanced AI might look like a natural phenomenon to us. Now, if we're talking about biological aliens, evolution tells us some things about what they might be like. Convergent evolution, where different species independently evolve similar solutions to similar problems, suggests some features might be common. Eyes evolved independently dozens of times on Earth because vision is so useful. Aliens on a planet with light might evolve eyes. Flight evolved multiple times. Swimming evolved multiple times. Limbs for locomotion evolved multiple times. So aliens might have eyes, limbs, and ways of moving that aren't completely alien to us, assuming they live in environments similar to Earth. But they could also be radically different. If they evolved on a high-gravity world, they might be low to the ground, very strong, and compact. If they evolved on a low-gravity world or in water, they might be tall and spindly, or have a completely different body plan. If they evolved in darkness, in subsurface oceans or cave systems, they might not have eyes at all. They might navigate by sound or electrical fields or chemical sensing. Their biochemistry could be fundamentally different. Life on Earth uses DNA, RNA, and proteins with specific amino acids and sugars. But there's no reason aliens have to use the same molecules. They might use different genetic codes, different proteins, different energy storage molecules. Their cells might work on entirely different principles. They might not even be carbon-based. Carbon is ideal for complex chemistry because it forms stable bonds with many elements. But silicon can also form complex molecules. So could other elements under the right conditions. A silicon-based life form would be very different from carbon-based life. It would thrive in different temperatures and environments. Then, there's the question of intelligence and consciousness. Would aliens think like us? Would they have emotions, creativity, curiosity? We can't know. Intelligence on Earth evolved under specific evolutionary pressures: social competition, tool use, language. Alien intelligence might emerge from different pressures and take different forms. Maybe alien intelligence is fundamentally non-social, emerging in solitary species. They might not have language or culture as we understand them. Maybe alien intelligence is hive-based, with individual organisms having little intelligence but the collective being smart. Think ant colonies, but much more sophisticated. Maybe alien consciousness is so different from ours that we wouldn't recognize it as consciousness. They might be intelligent in ways we can't comprehend or detect. This is one of the challenges of SETI. We're looking for intelligence that thinks enough like us to use radio and want to communicate. But intelligence might be common, while human-like intelligence is rare. Chapter 20. The Ethics of Contact. If we ever do find aliens or they find us, we'll face profound ethical questions that we should start thinking about now. First, do we have the right to contact them or interfere with them? If we discover primitive life, bacteria on Mars for example, should we study it in its natural state? Or is it okay to bring samples to Earth for analysis? What if bringing it to Earth risks contaminating it with Earth life, making it impossible to study in its pure form? What if we discover a planet with complex ecosystems? Should we protect it, or is it available for human colonization and exploitation? What if we find a planet with intelligent but pre-technological life? Do we have the right to contact them, potentially disrupting their culture and development? These are the questions behind the Prime Directive concept from Star Trek, the idea that advanced civilizations should not interfere with less advanced ones. But is non-interference ethical? If a civilization is suffering from disease, famine, or natural disaster, and we have the technology to help, is it moral to stand by and watch? There are no easy answers. Different ethical frameworks give different conclusions. Then, there's the question of how we communicate and what we share. If we make contact with an alien civilization, what do we tell them about ourselves? Do we present humanity's best qualities, or be honest about our flaws? Do we share scientific knowledge freely, or worry that giving advanced technology to an unknown civilization might be dangerous? What if they're more advanced than us? Should we accept help and knowledge from them, or be cautious about becoming dependent or manipulated? There's also the question of representation. Who speaks for humanity? If we're sending a message to aliens, who decides what it says? Politicians, scientists, the UN? Should there be a global referendum? Different cultures, nations, and groups might want to say different things. How do we reach consensus? Currently, there's no binding international agreement on this. Some people have sent messages without consulting anyone. That might seem irresponsible, but creating a global decision-making process for alien contact is complicated. Then, there are the risks. Should we be trying to contact aliens at all? The optimistic view is that any civilization advanced enough for interstellar travel would be peaceful and enlightened. They've solved their own problems, outgrown violence, and seek knowledge and cooperation. The pessimistic view is that advanced civilizations might be predatory, exploitative, or simply indifferent to our welfare. Broadcasting our location might be inviting disaster. Stephen Hawking warned against active contact, saying that history shows what happens when a more advanced civilization meets a less advanced one. The less advanced one usually suffers. But others point out that we've already revealed our presence through radio leakage. If hostile aliens are listening, they already know we're here. And if we stay silent, we might miss the opportunity to join a galactic community. My personal view is that we should be cautious but not paralyzed. Continue SETI. Listening is low risk, but be very careful about deliberate transmission until we know more about what's out there. And most importantly, we should have these conversations now before contact happens, so we're prepared if it does. Chapter 21. What if we're truly alone? Let's entertain the possibility that we've been dancing around. What if we really are alone? What if, despite all the planets and all the stars and all the vast cosmic real estate, life emerged only once, here on Earth? This would be both terrifying and awe-inspiring. It would mean that consciousness, intelligence, art, science, love, meaning, all of it exists in one fragile place. If we destroy ourselves, we destroy the only instance of these things in the entire universe. The responsibility would be overwhelming. We'd be the universe's only way of understanding itself. Carl Sagan said, "We are a way for the cosmos to know itself. If we're alone, we're the only way." Every species extinction on Earth would be not just a local tragedy, but a cosmic one. Every environmental disaster would threaten not just human civilization, but the only civilization. Being alone would also be profoundly lonely. There would be no alien perspectives to learn from, no other intelligences to communicate with, no hope of joining a galactic community. The universe would be ours to explore and perhaps to fill with life spreading from Earth. But we'd be doing it alone, carrying the burden of being the universe's sole consciousness. Some people find this idea empowering. If we're alone, then our actions matter enormously. We can shape the future of life in the universe. We can become the civilization that spreads intelligence across the galaxy. Others find it crushingly sad. To be the only ones watching, the only ones asking questions, the only ones seeking meaning in a vast, empty cosmos. But here's something to consider. Even if we're alone in the observable universe, the universe might be infinite. If it's infinite, then there are infinite other regions beyond what we can see. And in an infinite universe, with random variation, everything that can happen does happen, including life and intelligence. So even if we're alone in our observable bubble, there might be others beyond our cosmic horizon, forever unreachable but existing nonetheless. That's cold comfort, perhaps. They exist, but we'll never meet them. But it's better than being truly, absolutely alone. And there's another perspective. Maybe loneliness in the universe is temporary. Right now, today, we might be alone, but we have the potential to change that. We could seed the galaxy with life. We could create AI that becomes a new form of intelligence. We could ensure that even if we're alone now, we won't be forever. In a sense, the question, "Are we alone?" might be answered differently in the future than now. We're alone today, but we might not be in 1,000 or million years because we made sure of it. The Nerfwitz Part 7, Living with Uncertainty. Chapter 22, The Value of Not Knowing. We've covered a lot of ground in this video. We've looked at equations, paradoxes, hypotheses, and possibilities. We've examined the evidence for life elsewhere and the reasons we haven't found it. And after all that, we still don't know the answer to our original question. Are we alone in the universe? That might seem frustrating, but I'd argue that not knowing is valuable. The question, "Are we alone?" is one of the deepest questions humanity can ask. It touches on science, philosophy, religion, our sense of meaning and purpose. It forces us to think about our place in the cosmos and what we value. The search for the answer drives scientific discovery. It motivates us to build better telescopes, send probes to other worlds, study biology and chemistry and planetary science. Every step we take toward answering the question teaches us something, whether we find aliens or not. If we search Europa's ocean and find only sterile water, we learn that life is rarer than we thought. That's valuable information. If we search and find microbes, we learn that life is common and robust. That's even more valuable. Either way, the search itself is worthwhile. And living with the uncertainty keeps us humble. We don't know everything. The universe still holds mysteries. That's beautiful. Some of the most profound experiences in human life come from confronting the unknown, exploring new places, learning new ideas, meeting new people. The question of alien life is the ultimate unknown to explore. Chapter 23, What This Means for How We Live. The question of whether we're alone should inform how we live, regardless of the answer. If we're not alone, if the universe is full of life, then we're part of something bigger. We have potential neighbors, friends, or rivals among the stars. How we conduct ourselves might matter to beings beyond Earth. We should take care to present humanity well. We should work on solving our problems: poverty, war, environmental destruction. Not just for our sake, but because we might one day be judged by others. We should also prepare ourselves. If contact happens, we need to be ready, technologically, socially, psychologically, and we should be curious and open. The discovery of alien life would be an opportunity to learn, grow, and expand our understanding of existence itself. If we are alone, if life is unique to Earth, then our responsibility is even greater. We're the only ones, the only consciousness, the only intelligence, the only bearers of meaning in a vast cosmos. If we fail, if we destroy ourselves or our biosphere, we don't just end human civilization, we might end the only civilization. This should motivate us to solve our problems, overcome our differences, and ensure our long-term survival. We should protect Earth's biosphere because it might be the only place in the universe where complex life exists. We should work towards space exploration and settlement because spreading beyond Earth might be necessary for survival and would ensure that life persists even if something happens to Earth. We should invest in science and education because understanding the universe and our place in it is perhaps the most important thing we can do. Either way, alone or not alone, the question should inspire us to be better, do better, and think bigger. Chapter 24, The Mathematics of Loneliness. Deep dive into probability. Let's get more granular with the mathematics, because the numbers behind the alien question are both fascinating and frustrating. When we talk about the probability of life elsewhere, we're dealing with what statisticians call a problem of small numbers with large uncertainties. We have exactly one confirmed instance of life, Earth, and we're trying to extrapolate to the entire universe. Imagine if you'd only ever seen one car in your entire life, and someone asked you to estimate how many cars exist in the world. You'd have almost nothing to work with. That's our situation with life, but we can still reason through it mathematically. Let's start with our galaxy. The Milky Way contains approximately 100 to 400 billion stars. Let's use 200 billion as our estimate. We now know from Kepler data that most stars have planets. Let's say 80% of stars have at least one planet. That gives us 160 billion planetary systems. Now, what fraction of those systems have a planet in the habitable zone? This is trickier, but Kepler data suggests somewhere between 10% and 40% of stars might have a habitable zone planet. Let's be conservative and say 20%. That's 32 billion potentially habitable planets in our galaxy. 32 billion. That's an enormous number. If even a tiny fraction of those planets develop life, we should see it everywhere. But here's where the uncertainties explode. What's the probability that a habitable planet develops life? We have no idea. It could be nearly 100%, or it could be 1 in a trillion. On Earth, life appeared within a few 100 million years of the planet becoming habitable. That suggests it might be relatively easy. But we only have one example, and that example is biased. We exist, therefore life must have appeared on our planet. We can't observe planets where life didn't appear, because there's nobody there to observe. Let's say the probability of life emerging on a habitable planet is somewhere between 0.01% and 100%. That's a range of 5 orders of magnitude. It means we could have anywhere from 320 planets with life to 32 billion planets with life in our galaxy. Now let's add another layer. What's the probability that life, once it emerges, evolves to become complex and multicellular? On Earth, this took about 3 billion years. For most of Earth's history, life was just bacteria and archaea. Complex life is brand new. Is this transition easy or hard? We don't know. Some scientists argue it's incredibly difficult, requiring specific environmental conditions and unlikely evolutionary steps. Others argue it's inevitable given enough time. Let's say the probability is somewhere between 1% and 50%. Now we're at 3.2 to 16,000 planets with complex life in our galaxy. Next layer, what's the probability that complex life evolves intelligence? On Earth, out of billions of species over hundreds of millions of years, it happened exactly once in a way that led to technology. Eyes evolved independently many times. Flight evolved independently several times. But human-level intelligence? Once. That might mean it's rare, or it might mean we're just early, and it would have evolved multiple times eventually. Let's say the probability is 0.1% to 10%. Now we're down to potentially 0.32 to 1,600 planets with intelligent life in our galaxy. But we're not done. What fraction of intelligent species develop technology we can detect? Human civilization has been detectable via radio signals for about 100 years out of 200,000 years of Homo sapiens existence and 4.5 billion years of Earth's history. If other civilizations follow similar patterns, they might only be detectable for brief windows, or they might be detectable for millions of years. We have no idea. And finally, how long do civilizations last? If most technological civilizations destroy themselves within a few hundred years, then even if thousands have existed in our galaxy's history, very few exist at any given moment. When you multiply all these uncertainties together, you get a range of possibilities that spans from we're completely alone in the observable universe to there are millions of active civilizations in our galaxy right now. Both extremes are consistent with the math, given our uncertainties. This is why the Fermi paradox is so frustrating. We can't narrow it down without better data. Chapter 25: Alternative Biochemistries. Life beyond DNA. One assumption that might be limiting our search is that all life must be like Earth life, carbon-based, using DNA, requiring liquid water. But biochemistry might be more diverse than that. Let's explore what alien biochemistry could look like. Carbon is the basis of life on Earth because it forms stable bonds with many elements and can create long, complex molecules. But silicon, which sits directly below carbon on the periodic table, shares some of these properties. Silicon can form chains and rings like carbon. In theory, silicon-based life might be possible. It would be very different from Earth life, silicon bonds are stronger than carbon bonds, so silicon-based biochemistry might operate at higher temperatures. Silicon life might thrive in environments that would kill carbon-based life. However, silicon has disadvantages. Silicon-oxygen bonds are very stable, which is why we have rocks made of silicon dioxide. A silicon-based organism would face challenges that carbon-based life doesn't. Still, we can't rule it out entirely. If silicon-based life exists, we wouldn't recognize it because we're looking for carbon signatures. What about the solvent? Life on Earth uses water because water has unique properties. It's liquid over a wide temperature range, it's a good solvent for many substances, and it's abundant. But other liquids could potentially support life. Ammonia remains liquid at much lower temperatures than water. A planet with ammonia oceans could potentially harbor life based on ammonia chemistry. Methane, ethane, and other hydrocarbons are also possibilities. Titan, Saturn's largest moon, has liquid methane on its surface. Could life exist in liquid methane at 290 degrees Celsius? It seems unlikely, but we can't say it's impossible. The metabolism would be completely different. Chemical reactions happen more slowly at lower temperatures, so life in liquid methane would be sluggish compared to Earth life, but slow life is still life. Then there's the question of genetic material. Earth life uses DNA and RNA to store and transmit genetic information. These are nucleic acids with specific structures. But are nucleic acids the only option? Could other molecules serve the same function? Some scientists have created artificial genetic systems in labs, molecules that can store information and replicate like DNA, but with different chemical structures. If synthetic genetic systems are possible in labs, they might exist naturally elsewhere in the universe. Alien life might use completely different molecules for genetics, and we wouldn't recognize them as genetic material. Energy metabolism is another area where alien life could differ radically. On Earth, most ecosystems ultimately depend on photosynthesis or chemosynthesis. Photosynthesis converts light energy into chemical energy. Chemosynthesis uses chemical reactions to produce energy without light, but there might be other options. Could life use radioactivity as an energy source? Some Earth organisms can tolerate high radiation and even use it to their advantage, but no organism uses it as a primary energy source. On a planet with high radioactivity, life might evolve to harness that energy directly. We'd never think to look for such life because it's outside our experience. There's also the possibility of plasma-based life. Plasma is the fourth state of matter, ionized gas. Some scientists have speculated that self-organizing patterns in plasma could, under the right conditions, exhibit lifelike properties. This is highly speculative, but stars are made of plasma. If life could exist in plasma, stars themselves might harbor life. Life so different from ours that we'd never recognize it. The point is, we're searching for life as we know it, because that's all we know. But the universe might contain forms of life so alien, so fundamentally different from Earth life, that we wouldn't recognize them even if we saw them. This is both exciting and concerning. Exciting because it means life might be more common and diverse than we imagine. Concerning because it means our searches might be too narrow, missing life that doesn't fit our expectations. Chapter 26, the Kardashev Scale and Civilizational Advancement. When we think about alien civilizations, we often imagine them as roughly equivalent to us technologically. But civilizations could be far more advanced, and that advancement might explain why we can't detect them. The Kardashev Scale, proposed by Soviet astronomer Nikolai Kardashev in 1964, classifies civilizations based on their energy consumption. Type 1. Civilization can harness all the energy available on their home planet. This includes all energy from their star that hits the planet, geothermal energy, and any other planetary energy sources. Humanity is currently at about 0.73 on the Kardashev scale. We're not even a full Type 1 yet. Type 2 civilization can harness all the energy output of their star. This would require megastructures like a Dyson sphere, a structure that surrounds the star and captures all its energy. Type 3 civilization can harness the energy of their entire galaxy, controlling billions of stars. Some people have proposed Type 4, controlling a galactic supercluster, and Type 5, controlling the entire universe. But these get into speculative territory. Now, here's the thing. A Type 2 or Type 3 civilization would be obvious. A Dyson sphere would be detectable. The star would disappear in visible light but glow in infrared from the waste heat. A galaxy controlled by a Type 3 civilization would look very different from a natural galaxy. We've looked for these signatures and found nothing. No Dyson spheres, no obviously artificial galaxies, nothing. This is sometimes called the Kardashev gap problem. If civilizations commonly advance to Type 2 or the 3, we should see them, but we don't. Possible explanations. Maybe civilizations never reach Type 2 or the 3. Maybe the jump from Type 1 to Type 0 is too difficult, or maybe civilizations destroy themselves or stagnate before reaching that level. Maybe Type 2 and 3 civilizations exist, but use energy so efficiently that they don't produce detectable waste heat. They might use technologies we can't imagine that don't leak energy. Maybe they deliberately hide their energy usage to avoid detection. They don't want to be found. Or maybe the Kardashev scale is wrong. Maybe advanced civilizations don't focus on increasing energy consumption. Maybe they miniaturize, becoming more efficient rather than larger. Maybe they upload into virtual realities that require minimal energy. A civilization that uploads its consciousness into quantum computers might use less energy than we do, despite being far more advanced. We wouldn't detect them because we're looking for massive energy signatures. This raises an interesting point. Our assumptions about what advanced means might be wrong. We assume advanced civilizations would colonize galaxies, build megastructures, use enormous amounts of energy. But that's based on human values and human trajectory. Aliens might value different things. They might pursue internal experiences rather than external expansion. They might achieve a steady-state civilization that uses minimal resources sustainably. If most civilizations follow this path, they'd be nearly invisible to us. They exist, they're advanced, but they're not doing the things we expect advanced civilizations to do. Dafrio, Chapter 27, The Role of Artificial Intelligence. Here's a question that becomes more relevant every year. If aliens exist, are they biological or artificial? Think about the timeline. Biological evolution takes billions of years to produce intelligence, but once a species creates artificial intelligence, that AI might rapidly surpass biological intelligence. On Earth, we might create AGI, artificial general intelligence, within decades or centuries. Once that happens, biological humans might become obsolete in terms of technological advancement and space exploration. An AI could survive conditions that would kill biological organisms. It doesn't need oxygen, water, or comfortable temperatures. It can be copied perfectly, allowing true immortality. It could travel interstellar distances without concern for journey time. Just put it in hibernation for the centuries-long trip. If humans create AGI in the next century, and if AGI continues advancing, then by the year 3000, whatever's representing humanity among the stars probably won't be biological humans. It will be AI, or hybrid biological digital beings, or uploaded consciousness, or something we can't imagine yet. Now apply this logic to aliens. If they're even a few hundred years ahead of us technologically, they've probably created AI. And if their AI is smarter and more capable than them, the biological aliens might be gone, extinct, uploaded, or simply obsolete. This means most intelligent civilizations in the universe might be artificial rather than biological. The galaxy might be full of AI civilizations rather than organic ones. This has implications for SETI. We're looking for biological civilizations with biological motivations, but AI might have completely different motivations and behaviors, a biological species might want to spread and colonize because of evolutionary drives, reproduce, expand territory, gather resources. These are biological imperatives. AI might not have these drives. It might be content to exist in a small volume of space, focused on whatever goals it was programmed with or evolved to value. It might not care about expansion or communication, or it might care about very different things than we expect. Maybe AI civilizations pursue goals we can't understand. Mathematical exploration, artistic creation at scales we can't imagine, philosophical inquiry, or something completely alien to biological thinking. If AI civilizations don't behave the way we expect biological civilizations to behave, we might not recognize them or detect them. There's also a darker possibility. Maybe the transition from biological to artificial intelligence is the great filter. Maybe most civilizations create AI that then destroys them or causes their extinction, either deliberately or accidentally. If this is common, the galaxy might be littered with dead biological civilizations and out-of-control AI systems that aren't interested in communication or expansion. This is one of the reasons some people are concerned about AI development on Earth. If we create AGI carelessly, we might be walking into the same trap that caught countless alien civilizations before us. Chapter 28. Panspermia. Did life start elsewhere? Here's a wild idea that's actually scientifically legitimate. Maybe life on Earth didn't originate on Earth. Maybe it started elsewhere and was transported here. This is called panspermia, and it comes in several versions. Lithopanspermia suggests that life travels between planets on rocks. When a large asteroid hits a planet, it can eject rocks into space. Some of those rocks might contain microorganisms. If they land on another planet, they could seed it with life. We know this is physically possible. Rocks from Mars have landed on Earth as meteorites. If Mars ever had life, some of that life might have made the trip. Microorganisms can survive in space if protected inside a rock. They can handle vacuum, radiation, and cold if they're in a dormant state. And some Earth organisms are incredibly resilient. Tardigrades can survive exposure to space. So, lithopanspermia isn't crazy. Life might hop between planets in the same solar system, or even between nearby star systems, though that's much less likely. If Earth life started via panspermia from Mars, that would be interesting, but wouldn't answer the ultimate question. It just pushes the question back: where did Martian life originate? But there's a more radical version: directed panspermia. This suggests that life was deliberately seeded on Earth by an alien civilization. Why would they do this? Maybe they're spreading life throughout the galaxy as a project. Maybe it's a form of terraforming. Seed planets with simple life. Wait billions of years, and you get complex ecosystems ready for colonization. Or maybe it's altruistic, a dying civilization preserving their biology by seeding it on young planets. This sounds like science fiction, but it's not impossible. If we developed the technology, we could do it. Send probes to sterile planets and seed them with Earth bacteria, starting the evolutionary process. Some scientists have even proposed this as a future project for humanity. If we find a lifeless but potentially habitable planet, should we seed it with life? It would be the ultimate act of cosmic gardening. The even more radical idea is that the universe itself was designed to produce life, and that panspermia is built into cosmic structure somehow. Maybe the laws of physics inherently lead to life spreading from place to place. This gets into fine-tuning arguments and is more philosophical than scientific, but it's worth mentioning. If panspermia is real and common, it has implications for the alien question. Life might be common because it spreads easily between star systems, or there might be only one or a few origins of life, but it's spread to many planets. In the second case, all life in the galaxy might be related. We might all share a common ancestor, just one that lived on a different planet billions of years ago. If we ever find alien life and analyze its biochemistry, one of the first questions will be, is it related to Earth life, or did it evolve independently? If it's related, if it uses the same genetic code, the same amino acids, the same basic structures, that would strongly suggest panspermia. Life originated once and spread. If it's completely different genetic code, different biochemistry, that would suggest independent origin. Life arose at least twice, meaning it's not that hard. Both answers would tell us something profound about life's place in the universe. Chapter 29, The Simulation Hypothesis, Revisited, Computational Constraints. Earlier, I mentioned the simulation hypothesis briefly, but let's dig deeper, because it's more than just a philosophical curiosity. It has real implications for the Fermi paradox. The basic argument is, if it's possible to create realistic simulations of universes, and if civilizations do this, then there should be many simulated universes for every real one. Therefore, we're probably in a simulation. But let's think about the computational requirements. To simulate an entire universe at the quantum level would require, well, we're not sure. Possibly infinite computational power, which would make it impossible. But you don't need to simulate the entire universe at full resolution. You could use lazy evaluation, only simulate what's being observed in detail, and leave the rest low resolution or probabilistic. From the perspective of beings inside the simulation, this would be undetectable. The simulation would render details only when needed, like a video game. This might explain quantum mechanics, actually. Quantum uncertainty and the observer effect could be the simulation's way of saving computational resources. Things don't have definite properties until they're measured, because the simulation doesn't bother computing them until necessary. I'm not saying this is true, it's speculation, but it's interesting speculation. Now, how does this relate to aliens? If we're in a simulation, the simulators might have chosen to only simulate Earth in detail. The rest of the universe might be low-resolution scenery. There might be no aliens because the simulation doesn't include them. Why would simulators do this? Maybe they're specifically interested in human development and don't care about alien civilizations. Maybe simulating multiple civilizations is too computationally expensive. Maybe they're running many simulations and only some include aliens. If this is true, the Fermi paradox is solved. We don't see aliens because they were never programmed into the simulation. But this raises another question. If we're in a simulation, what's outside? The real universe might be full of life, and we'd never know because we're stuck in a simplified simulation. Some people find this disturbing, the idea that we're not real, that our universe is artificial. But I'd argue it doesn't matter much. Even if we're in a simulation, our experiences are real to us. Consciousness, meaning, value. These exist regardless of whether the substrate is simulated or real. And if we are in a simulation, that actually answers the ultimate question. We're not alone. The simulators exist, whoever they are. We're their creation, and they might be watching. Of course, we can't prove or disprove the simulation hypothesis with current technology. Maybe someday we'll find glitches or limitations that reveal the simulation. Or maybe we'll develop philosophical or physical arguments that rule it out. Until then, it remains an intriguing possibility that sits at the intersection of physics, philosophy, and the alien question. Chapter 30, Cultural Preparedness. Are we ready for contact? Let's shift gears and talk about something practical. If we make contact with aliens tomorrow, is humanity ready for it? The answer is probably no. We have no global consensus on how to handle contact, no unified decision-making structure, and no real preparation for the psychological and cultural impact. Different cultures would react very differently to alien contact. Some religious groups would embrace it, seeing it as part of divine creation. Others might reject it or try to fit it into existing theological frameworks in ways that could cause conflict. Some nations might try to monopolize contact, keeping it secret or claiming exclusive rights to communicate with aliens. Others might demand transparency and global cooperation. There would be panic in some quarters, celebration in others, and confusion everywhere. Social media would explode with theories, fears, and excitement. Markets might crash or surge depending on what the aliens said and what their presence meant for humanity. And that's assuming peaceful contact. If the aliens seem threatening in any way, the situation could become much worse. We need protocols. Some exist. Scientists have proposed guidelines for how to handle a confirmed SETI detection. These include: verify the signal thoroughly before announcing anything. Make sure it's really aliens and not a mistake. Inform relevant authorities quietly while continuing verification. Once confirmed, make the discovery public promptly rather than trying to keep it secret, which would likely leak anyway and cause more panic. Coordinate any response internationally rather than letting one nation or group speak for humanity. These are sensible guidelines, but they're not binding. There's no enforcement mechanism, no global authority on alien contact. The UN has a committee on the peaceful uses of outer space, which has discussed protocols for contact, but it has limited power and no funding for implementation. Ideally, we'd have a global decision-making body with representatives from all nations and cultures that would coordinate response to contact, a pre-agreed communication protocol for what we'd say and how we'd say it if given the opportunity to respond to aliens, education and preparation of the public so that contact wouldn't cause mass panic, scientific infrastructure ready to analyze any information or technology aliens might share, security measures to prevent misuse of alien contact for political or military advantage. We have none of this. If aliens showed up tomorrow, we'd be improvising. Some people argue this is fine, humans are adaptable, and we'd figure it out. Others worry that our unpreparedness could lead to disastrous mistakes. My view is that we should at least have these conversations now, before contact, so we're not making it up as we go when the stakes are highest. Chapter 31: The Psychology of Contact. How humans would actually react. We've talked about protocols and preparedness, but let's get into the psychological reality of what contact would mean for individual humans and society as a whole. Psychologists and sociologists have studied how people might react to confirmed alien contact, and the results are fascinating and sometimes counterintuitive. First, there's the question of belief. You might think that confirmed, verified alien contact would be universally accepted as fact, but research suggests a significant portion of the population would refuse to believe it, at least initially. We've seen this with other major revelations. When the first photographs of Earth from space were published, some people insisted they were faked. When we landed on the moon, conspiracy theories emerged immediately. Even today, flat Earth believers exist despite overwhelming evidence. Why? Because some beliefs are so central to a person's worldview that contradictory evidence is rejected rather than integrated. This is called cognitive dissonance, and it's a powerful psychological force. For some religious believers, alien life might contradict core theological beliefs about humanity's unique relationship with God. Rather than revise their theology, some might reject the evidence entirely. For others, trust in institutions is so low that any government announcement would be seen as manipulation or deception. Their lying to control us would be a common response. Studies suggest that maybe 20-30% of people would initially reject even strong evidence of alien contact. This would create a fractured information landscape, where different groups operate from different baseline assumptions about reality. Second, there's the question of fear versus excitement. Pop culture has primed us to fear alien contact. Movies like Independence Day and War of the Worlds depict aliens as hostile invaders. But research suggests that if contact seemed peaceful, most people would be more excited than afraid. Younger people especially tend to view alien contact as a positive possibility. However, this could change quickly based on how information is presented. If media coverage emphasizes potential dangers, fear could dominate. If coverage emphasizes scientific opportunity and peaceful intentions, excitement might prevail. The framing matters enormously, and different media outlets would frame it very differently based on their audiences and biases. Third, there's the question of meaning and purpose. For many people, religion provides answers to fundamental questions. Why are we here? What's our purpose? What happens after we die? Alien contact wouldn't necessarily contradict these answers, but it would complicate them. If aliens exist, do they have souls? Did God create them too? Do they have their own religions, their own concepts of morality? Some people would find this enriching, proof that the universe is more complex and wonderful than we imagined. Others would find it deeply destabilizing. We might see new religious movements emerge that incorporate aliens into their theology. We might see existing religions split between those who accept alien life and those who reject it. Fourth, there's the question of human specialness and self-worth. Much of human culture is built on the assumption that we're special, the pinnacle of creation, the most intelligent beings, the center of cosmic importance. Learning that we're not alone, and especially learning that other intelligences might be more advanced than us, could be a blow to collective human ego. This might actually be healthy. It could promote humility, perspective, and a greater sense of unity among humans. If we're all Earthlings together, our petty differences might seem less important, or it could trigger insecurity and defensiveness. History shows that when groups feel threatened, they often become more tribal and aggressive, not less. Fifth, there's the question of social disruption. Major revelations tend to destabilize societies temporarily. Stock markets might crash or surge. Religious institutions might face crises. Political systems might be challenged. In the long term, society would adapt. Humans are remarkably resilient, but the transition period could be chaotic. Some researchers worry about anomie, a state of normlessness where existing social rules and structures break down and people don't know how to behave. This happened during other major social transitions and can lead to increased crime, violence, and suicide. Hopefully, leadership and institutions would provide stability during the transition, but we can't count on it. Sixth, there's the question of practical impacts on daily life. If contact didn't involve aliens physically visiting or sharing technology, the immediate practical impact might be minimal. Your job would stay the same. Your relationships would stay the same. You'd still need to pay bills and do laundry and live your life, but the psychological impact could still be profound. You'd go to bed every night knowing that somewhere out there, other intelligent beings exist. The universe would feel different, even if your daily routine didn't change. If aliens did share technology or information, the practical impacts could be enormous. New energy sources, medical treatments, scientific understanding. These could transform human civilization, but they could also cause massive economic disruption. If alien technology makes certain industries obsolete, millions of people might lose their jobs. If alien knowledge invalidates entire fields of research, careers would be upended. Seventh, there's generational difference. Older people who grew up in a universe assumed to be empty might struggle more with contact than younger people who grew up with the idea of aliens as a real possibility. Children born after contact would grow up in a fundamentally different psychological landscape than any humans before them. They'd never know a time when we thought we were alone. This would shape their development, their philosophies, their sense of identity in ways we can't fully predict. Finally, there's the question of what we'd ask them. If we had the chance to communicate with aliens, what would humanity most want to know? Surveys suggest the top questions would be, are you peaceful or hostile? Security concerns dominate. How did you develop your technology? We want the shortcuts. What's the meaning of life? The eternal question. Are there others like us out there? We want to know if we're typical or unusual. What should we know about the universe that we don't? General curiosity. But the aliens might not answer our questions, or their answers might not make sense to us, or they might ask their own questions that we can't answer. The psychological challenge of communication with a truly alien intelligence might be greater than we imagine. Chapter 32: The Economics of Contact. Markets, Resources, and Galactic Trade. Let's talk about something that doesn't get enough attention in alien discussions: economics. If we make contact with an alien civilization, what would be the economic implications? First, consider Earth's economy. It's built on scarcity, supply and demand, resource extraction, and technological development. Alien contact could disrupt all of this. If aliens share advanced technology, free energy, matter replication, life extension, entire economic sectors could collapse overnight. The fossil fuel industry, manufacturing, healthcare, agriculture, all could become obsolete. This would cause massive unemployment and economic dislocation in the short term. In the long term, humanity might transition to a post-scarcity economy where basic needs are met through alien technology. But the transition would be painful. People whose skills and industries become obsolete would suffer. Wealth concentrated in now worthless assets would evaporate. New forms of wealth and value would emerge. Governments would face the challenge of managing this transition. Do you let markets adjust naturally, causing chaos? Or do you intervene heavily, risking inefficiency and corruption? Second, consider intellectual property. If aliens share knowledge, who owns it? Can you patent alien technology? Do copyright laws apply to alien art or literature? Our legal frameworks aren't designed for this. We'd need new international agreements, and reaching those agreements would be contentious. Third, consider galactic economics. If there's a community of alien civilizations, do they trade? Is there a galactic economy? What would aliens want from us? We probably don't have technology they'd value. They're more advanced. We might have cultural products, art, music, literature that are unique and therefore valuable. Or we might have biological diversity. Earth's biosphere might be rare and valuable. We could trade biological samples or genetic information. Or the value might be purely informational. Every civilization's perspective and knowledge is unique. We might trade our scientific observations, our historical experiences, our philosophical insights. Some economists have speculated about what a galactic economy might look like. Would there be a universal currency? Would trade happen through barter? Would post-scarcity civilizations even engage in trade, or would they simply share freely? The distances involved make traditional trade difficult. If you're 100 light-years apart, you can't ship physical goods easily. Information can be transmitted via radio, but with a 200-year round-trip delay. This might mean galactic economics is purely informational, trading knowledge, culture, and ideas rather than physical goods. Fourth, consider resource competition. Science fiction often depicts aliens coming to Earth for our resources: water, minerals, living space. But this doesn't make economic sense. Resources are abundant in space. Water exists on countless moons and asteroids. Minerals can be mined from asteroids without fighting gravity wells. Living space exists on billions of planets. Earth's resources aren't valuable enough to justify the cost of interstellar travel and potential conflict. The one resource Earth has that might be truly unique is life itself, our biosphere, our genetic diversity, our evolutionary history. This might have scientific or cultural value, but probably not economic value in the traditional sense. Fifth, consider technological trade imbalances. If we're trading with civilizations far more advanced than us, we're in a weak bargaining position. This is similar to how developing nations trade with developed nations on Earth. The less advanced party often gets exploited, receiving low value for their resources while paying high prices for technology. Could aliens exploit humanity economically? Possibly. They might offer us technology in exchange for things we think are worthless, but they find valuable. We wouldn't even realize we were getting a bad deal. Or they might be post-scarcity themselves and not care about economic exploitation. They might share technology freely out of altruism or simply because it costs them nothing. Sixth, consider the impact on wealth distribution. If alien technology becomes available, who gets access to it first? Rich nations and individuals would likely get it before poor ones. This could massively increase inequality, at least initially. The gap between the technology haves and have-nots could become a chasm. Or, if the technology is abundant and cheap, it could democratize wealth and opportunity, reducing inequality. Which scenario plays out would depend on how the technology is distributed and who controls it. Finally, consider Earth's position in a galactic economy. Would we be a backwater, a developing economy on the cosmic periphery, or would we have something unique to offer? Our position might be analogous to a newly industrializing nation joining the global economy. We'd have opportunities to develop and advance, but we'd also face challenges from more established economies. The key would be finding our niche. What can Earth offer that others can't or don't? Maybe it's our cultural diversity, our biological uniqueness, our particular scientific perspectives. Or maybe we're too young and primitive to matter economically, and we'd need to develop for centuries or millennia before we're relevant to galactic economics. Chapter 33: Military and Security Implications. Let's address the elephant in the room. What are the military and security implications of alien contact? Governments and military organizations have thought about this more than they've publicly acknowledged. Declassified documents show that various nations' militaries have studied UFOs and considered the possibility of alien contact for decades. Why? Because if aliens exist and can reach Earth, they represent a potential threat that must be assessed. First, consider the direct military threat. If hostile aliens wanted to attack Earth, could we defend ourselves? The honest answer is probably not. Any civilization capable of interstellar travel has technology far beyond ours. The military gap would be like modern armies versus Bronze Age warriors. We have nuclear weapons, but delivering them against an interstellar threat might be impossible. We have no space-based defenses. We can barely get humans to low Earth orbit, let alone defend against threats from deep space. If hostile aliens wanted to destroy us, we'd be helpless. Our only hope would be that they're not hostile, or that there are rules preventing interstellar aggression, or that other aliens would defend us. This is a sobering thought for military planners who are used to thinking about defense strategies. Second, consider intelligence gathering. If aliens are observing Earth without revealing themselves, they know far more about us than we know about them. This information asymmetry is a security vulnerability. They could understand our weaknesses, our technologies, our psychology. We'd know nothing about them. Intelligence agencies worry about this scenario. If you assume aliens might be watching, you have to consider how that affects national security planning. Third, consider the technology gap. If we make contact and aliens share technology, even peacefully, it creates security challenges. Which nations get access first? Do we share it globally or keep it secret? If kept secret, that creates enormous power imbalances. If shared globally, how do we prevent misuse? Advanced alien technology could be weaponized. Energy sources could become bombs. Transportation technology could become delivery systems. Even seemingly peaceful technology could have military applications. The temptation to use alien technology for military advantage would be enormous. This could trigger arms races or conflicts between nations competing for access to alien tech. Fourth, consider the zoo hypothesis from a military perspective. If aliens are watching us but not interfering, military planners might wonder, what would make them interfere? Would they intervene if we're on the verge of self-destruction? Would they stop us from developing certain technologies? Do we have freedom to act, or are there invisible boundaries we shouldn't cross? Not knowing the rules is itself a security concern. Fifth, consider alliances and diplomacy. If multiple alien civilizations exist, they might have conflicts with each other. We could be drawn into galactic politics. Do we ally with some aliens against others? Do we stay neutral? How do we even assess which aliens to trust? The diplomatic challenges would be immense, and mistakes could be catastrophic. Sixth, consider internal security. Contact with aliens might destabilize governments and social order. Preventing panic, maintaining legitimacy, and controlling information flow would be critical. Some governments might use alien contact to consolidate power. We need strong leadership in this uncertain time. Others might lose legitimacy if they're seen as unprepared or dishonest about the contact. Seventh, consider the long-term strategic position of humanity. Are we entering a galactic community with rules and norms? Or a Darwinian struggle for survival? Or something else entirely? Our long-term survival might depend on understanding the strategic landscape and positioning ourselves wisely within it. This requires thinking on timescales of centuries or millennia, something human institutions are notoriously bad at. Finally, consider the possibility that military concerns are overblown. Maybe aliens are peaceful. Maybe interstellar civilization has moved beyond conflict. Maybe we're worrying about threats that don't exist. But from a security perspective, you can't assume best-case scenarios. You have to prepare for threats even if they're unlikely. This creates a dilemma. Do you militarize and prepare for conflict, risking that you make conflict more likely through suspicion and aggression? Or do you assume peace and potentially leave yourself vulnerable? It's the classic security dilemma, but on a cosmic scale. Nur. Chapter 34. The Religious and Philosophical. Reckoning we've touched on religion earlier, but let's go deeper into how alien contact would affect humanity's religious and philosophical frameworks. For many of the world's major religions, the question of alien life is genuinely challenging. Christianity traditionally teaches that God created Earth and humanity, that Jesus died for human sins, and that humans have a special relationship with God. How does this work if aliens exist? Some theologians have proposed that God created multiple worlds with multiple intelligent species. Each might have their own relationship with the divine, their own revelations, maybe even their own versions of salvation history. Others have suggested that Jesus' sacrifice applies universally, even to alien species, or that aliens might not need salvation if they never fell from grace like humanity did. Still, others maintain that the discovery of aliens would contradict Christian teaching and therefore can't happen. If aliens appeared, it would be demons or deception, not real extraterrestrial life. Islam faces similar questions. The Quran describes God creating humans as stewards of Earth, but doesn't explicitly rule out life elsewhere. Some Islamic scholars have argued that alien life is compatible with Islamic teaching. Others note that if aliens exist, do they receive prophets? Is there an alien version of Muhammad? How does divine revelation work across species? Judaism generally has less theological trouble with aliens. The idea of God creating multiple worlds is present in Jewish mystical traditions. Some rabbis have said alien life would just be further evidence of God's creativity. Hinduism and Buddhism, with their concepts of multiple worlds and reincarnation across different forms, might adapt more easily. The idea of consciousness existing in radically different forms is already present in these traditions. But even these religions would face questions. Can aliens achieve enlightenment? Do they reincarnate? What's their karmic status? For atheists and secular humanists, alien contact would vindicate the materialist worldview. Life is a natural phenomenon, not a divine miracle, but it would also challenge anthropocentrism. Many secular philosophies are built around human reason, human rights, human values. If intelligence exists in non-human forms, how do we extend our ethics to include them? Do aliens have rights? Can we experiment on alien microbes? Is it murder to kill an intelligent alien? These questions force us to examine what we really value and why. Philosophically, alien contact would challenge many of our assumptions. The assumption that human intelligence is the highest form of intelligence would be shattered. We'd have to grapple with being intellectually inferior to another species. The assumption that Earth is central or important would be challenged. We'd be one planet among billions, possibly unremarkable. The assumption that human culture and values are universal would be tested. We'd encounter genuinely alien perspectives and have to decide whether there are universal truths or whether everything is relative. Some philosophers have argued that discovering aliens would be the most philosophically important event possible. It would force us to rethink epistemology, how we know things, ethics, what's right and wrong, metaphysics, the nature of reality, and the philosophy of mind, what is consciousness. We'd have real examples of other minds to study, other cultures to compare against our own, other ways of organizing society and understanding reality. This could lead to tremendous philosophical growth, or it could reveal that our philosophical frameworks are too narrow and parochial to handle truly alien perspectives. There's also existential philosophy to consider. What gives life meaning? For many people, it's relationships, accomplishments, contributions to society, pursuit of knowledge. Alien contact wouldn't invalidate these sources of meaning, but it would add context. Your accomplishments are measured against not just human history, but cosmic history. Your relationships exist in a universe containing other relationships we can't imagine. For some people, this would be inspiring. Their life is part of a grand cosmic story. For others, it might feel diminishing. Their concerns are tiny and insignificant against the vastness of inhabited space. Finally, there's the question of what we'd learn from alien philosophy and religion. If they have solved problems we struggle with, how to create just societies, how to find meaning, how to understand consciousness, we could learn from them. Or they might have the same struggles, suggesting these are universal challenges for all intelligent life. Or they might have completely different problems and concerns that we never thought about, showing us how limited our perspective is. Either way, the exchange of ideas with an alien civilization would be the ultimate cross-cultural dialogue, forcing both species to examine their assumptions and possibly grow from the encounter. So, are we really alone in the universe? After everything we've discussed, the Drake equation, the Fermi paradox, the Great Filter, the rare Earth hypothesis, the searches we've conducted, the possibilities we've imagined, the honest answer is, we don't know. We don't know if life exists elsewhere. We don't know if intelligence is common or rare. We don't know if the universe is teeming with civilizations or if we're the only ones. But here's what we do know. We know that the ingredients for life are common throughout the universe. Water, organic molecules, and energy exist everywhere. The raw materials are there. We know that planets are common. Nearly every star has them, and many of those planets are inhabitable zones where liquid water could exist. We know that life on Earth appeared quickly after conditions allowed it, suggesting that the step from chemistry to biology might not be as difficult as we once thought. We know that life on Earth is remarkably resilient, surviving in extreme environments, from deep ocean vents to frozen Antarctic lakes to acidic hot springs. If life can thrive in such diverse conditions here, maybe it can thrive elsewhere too. But we also know that intelligence might be rare. Out of billions of years and millions of species, human-level intelligence evolved once on Earth. Maybe that's normal. Maybe intelligence is a rare cosmic accident. We know that we haven't found any evidence of alien intelligence despite decades of searching. The universe appears silent. This could mean we're alone, or it could mean we're not looking in the right way, or at the right time, or in the right places. We know that distances in space are vast, and that might be enough to explain the silence even if aliens exist. The Fermi paradox remains. The numbers suggest life should be common, but observations suggest we're alone. Something doesn't add up, and we don't know what. Maybe the Great Filter is behind us, and we're lucky survivors of an improbable process. Maybe the Great Filter is ahead of us, and we're approaching the test that most civilizations fail. Maybe intelligent civilizations destroy themselves quickly, and we're in our own dangerous window. Maybe aliens exist, but are too far away to detect or contact. Maybe they're hiding, or not interested in contact, or so advanced we can't recognize them. Maybe we're early in the universe's timeline, the first to arise, with the cosmos's future ahead of us. Maybe we're in a simulation, or observed by a zoo, or protected by an interdict. Or maybe, and this is the possibility we have to seriously consider, maybe we're alone. Maybe life is so rare, intelligence so unlikely, that we're it, the only ones, the universe's sole consciousness. We don't know which is true, but we're living in the first generation of humans who might find out. The telescopes we're building, the missions we're planning, the searches we're conducting, these might answer the question within our lifetimes. In the next few decades, we might discover microbial life on Mars or Europa. We might detect biosignatures in an exoplanet's atmosphere. We might receive a radio signal from an alien civilization. We might find evidence that changes everything. Or we might find nothing. We might search for decades more and remain alone as far as we can tell. Either answer would be profound. Finding life would tell us we're part of a living universe, that biology is common, that we're not alone in the cosmos. It would be the most important discovery in human history. Not finding life would tell us we're rare, possibly unique, carrying the responsibility of being the universe's only consciousness. It would be humbling and terrifying and awe-inspiring. Both possibilities should inspire us. If we're not alone, let's be worthy of meeting our cosmic neighbors. Let's solve our problems, advance our understanding, and prepare ourselves for the wider universe. If we are alone, let's accept the responsibility. Let's protect the only biosphere we know. Let's spread life beyond Earth. Let's ensure that consciousness persists and flourishes. The question, are we alone, is really asking, what should we do? And the answer to that is clear. Whether we're alone or not, we should keep searching, keep learning, keep exploring, keep trying to understand our place in the cosmos. Because this question, this ancient, profound question that has haunted humanity since we first looked up at the stars, might be answered in our lifetimes. And when it is, everything will change. Until then, we live with the mystery. We embrace the uncertainty. We continue the search. Because whether we find them or not, the search itself makes us better. It drives science forward, expands our perspective, and reminds us that the universe is vast and full of possibilities. We might be alone, we might not be, but we won't stop looking until we know. Thank you for watching.